What's up, gamers? Okay, today we have Lab 5, magnetic braking with Faraday's Law for Physics 2212, and let's get right into it. I just had some cheesecake. So, a bit of an introduction to this lab. The purpose of this lab is to observe the interactions between a bar magnet and aluminum foil tube and understand the relationship of Lenz's law and Faraday's law as it applies to magnetic flux. And a bit of a sneak peek here. The results of this lab are as follows. So the average time we had in the 5 trials was 2.13 seconds, and the time we received from the computational model is 3.569 seconds. It's higher. So apart from Lenz's law and Faraday's law, some other fundamental physics properties and equations we do need to understand are magnetic flux, which is just the, in this case, it's just the product of magnetic field and area. Ohm's law, which is V equals IR, and force in the loop, which it's I times area, which is 2 pi R, times magnetic field, and sine of theta. So the procedure is going to be this little image right here, and the procedure is very simple. We simply just grab a bar magnet and drop it down the tube. This tube being made of aluminum, and record the time each time. And the 5 trial average was 1.72 seconds. The tube length itself was 0.3 meters. The full length was 0.006 meters. The inner radius was 0.016 meters. And the outer radius is 0.022 meters. So apart from this actual conventional lab itself, we also made a code version, a computational model of this all, using, if I recall correctly, the where are you? The value for magnetic field from lab 3. And the code right here, this right here just sets up the tube itself with the radii, the exact same as our in-person one. Our parameters are right here, the simulation. Nothing was changed here, of course. This next 7 right here is creating the bar magnet itself, setting its, here we go, the magnetic moment right here, as well as its mass, and just making it a cylinder. Its radius right here. The initial conditions were time equals 0, and we're setting up the velocity vector. And this next equation right here is just actually calculating the magnetic field of the bar, and this next one right here calculates the magnetic flux of the bar. And it's just using this previously mentioned equation from earlier on. And then the simulation loop, it's just it's visualizing and predicting its motion. Just a bit of an if statement right here. And this right here, it's for the extra, because when we drop this bar magnet, it's under the influence of the magnetic force it generates to the tube, as well as the gravitational force it experiences by being on Earth. Okay, and right here, same thing as before. Magnetic force on the magnets, net force on the magnet, which is F grav plus F magnetic, its velocity and position, so on, so forth. And here is where we have the end of the code. And our computation results are as follows, as we received the in the results in the beginning. It was 3.569 seconds, which is slower than the in-person result, which is just due to in person everything won't be perfect, versus the computational model can give you a formula-based concrete experimental setting. And here's my little model. And before we begin the discussion, let's just acknowledge here the computational model was slower than the in-person model. Understand that. And magnetic force is capable of resisting the effects of gravitational force to make the magnet fall slower through the tube. And let's get into the discussion. So immediately, some sources of error were extra friction from handling the tube and magnet, timing errors when clicking start and finish, rounding errors from centimeters to meters, small ones. And as well, anyone who really wants to really grade my video, the system is the tube and the magnet. There we go. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnets change? It's quite simple. So nearly 0 resistivity would cause nearly 0 resistance, because those values are directionally proportional. Looking at Ohm's law, if there is near 0 resistance, there's an even larger induced current. This would mean that the magnet would take longer time to fall since it has to counter a stronger force on the loop. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Now, if holes or slots were cut into the tube, this would interrupt the flow of the ring currents, causing them to increase in value. And once again, because of Ohm's law, the opposite of the situation above would occur. The magnet would fall faster through the tube, as less force means less time for the magnet to fall through the tube.